say, over the complex numbers. And the main invariants of interest to us are, well, the Picard group, the Référence group, and these cones you've heard about yesterday and the day before, the effective cone and the ample cone. And I'm talking about the closures of the corresponding effective cone. These are closed cones. Now, in the surface case, they're dual. So for cubic surfaces, Del Pezzo surfaces we're looking at, so these are two dual cones. And finally, the canonical class, it's just a vector in the lattice, if you like, in the Référence lattice. And the standard example is a hypersurface of dimension bigger or equal than 3. The Picard of X is Z. It's generated by the hyperplane class, and there is a computation of the canonical class. So it's a multiple of the generator, and it's this particular multiple. Number of variables minus the degree and with a minus sign. And in dimension 1, if you have a cone, not many choices. So the effective and the ample cone are the same, and they're spanned by the hyperplane class. Now, in case of surfaces, so a hypersurface in P3, in particular cubic hypersurface, we know that over the complex numbers, the rank of the Picard group is 7. So P2 blown up in 6 points, you've heard about it. But over the rationals, it need not be 7. And the rank can range from 1 to 7. Okay? Now, so you're given a cubic surface, some equation, homogeneous equation, 4 variables, degree 3. How do you determine this rank, R? I mean, it's doable. I know how to do it in principle, but it would be nice to have a routine in Magma doing this reliably, yes? So one of the exercises. Another thing of relevance in number theoretic questions is how do you compute this effective cone? And again, over the complex numbers, we know what it is. You've heard about it. It's spanned by the 27 exceptional curves, lines in the anti-canonical embedding, and the standard embedding into P3. So, and now you are looking at, what happens over non-closed fields. So you take Galois invariance. And so today in Professor Hassett's lecture, you'll discuss in more detail, or he will discuss in more detail, what happens over non-closed fields. All right? So compute this effective cone. It's all doable, but somebody should do it. Now, what happens when the cubic surface is singular? I mean, we allow mild singularities, rational double points. Then there is a minimal desingularization. So compute the effective cone for that. And if you work over non-closed field, again, the rank of the Picard group can be from here to there. And so implement algorithms computing these things. So here is an example, one of the easiest examples. Look at this particular, oh, it's not to the 4, sorry. This is a 3. So forget this 4, it's a 3. It's a sum of cubes equals 0. So then the Picard group of X over the rationals, over Q, is of rank 4. And you compute that effective, or we computed that the effective cone has 9 generators. You just write down these explicit 9 generators and write down the explicit Picard group. All right. Now, why would you want to do that? Well, so there are these conjectures about the asymptotic of rational points of bounded height. And some of the ingredients, as we will see later on, are the rank of the Picard group and the effective cone and some numbers derived from that. And you can obviously run these things on computers, test numerically, so plug in numbers, so you get your plots, and then you want to match your numerical data, experimental data with the theoretic predictions. And then you need to compute this kind of invariant. So, and that's sort of one of the first steps in understanding what could be true in the general setup. Now, let's look, the 4 was there for a reason previously. I mean, in fact, let's look at a smooth surface of degree 4 in P3. So this is a K3 surface, And it's known that over the complex numbers, again, the rank of the Picard group can be anywhere from 1 to 20. So what is it? There are some examples. You can compute these ranks in cases, some explicit equations, and those computations are based on some special structures. Maybe you exhibit an elliptic fibration, and then maybe there are like very explicit lines, explicit rational curves that you can control, and you show that they're kind of independent of the Picard group. In any event, so those questions have been studied. It's not straightforward to produce examples of these surfaces over the rationals with prescribed Picard numbers, R's, say over the ground field, and also it may change over Q bar. Again, in this case, even over the closure of Q, you could have situations where the rank is between 1 and 20. So it's not at all the case, like for cubic surfaces that over Q bar, the rank is always 7. All right, so now the obvious question is there even a theoretical, effective way, so some abstractly effective way to compute this rank? I don't know. So that would be the question. How to determine this R effectively? Yes? Well, that's what I was saying. So over the ground field Q or over Q bar, it can be between 1 and 20. I'm not completely sure. I think in this case, even over Q. But in any event, in this case, it's geometric of rank 1, and then it's also rank 1 over Q. So there is no choice. It's easier, in a sense, to get to control the rank, say, over non-closed fields than geometrically. Yeah. So now, how to determine R effectively? That's quite tricky, and it is known that if you have a family, then the rank jumps sort of rather wildly, uncontrollably, and the jump of the rank has to do with occurrence of sort of additional curve classes, if you like, so curves, and rational curves that suddenly appear on your hypersurface of degree 4, and you don't know in which degrees they can appear, so the degrees can jump, and so this question is so interesting geometrically and also arithmetically. In any event, so here we have our cones, ample cone and effective cone. We don't know how to compute it in all cases, but it is important for us and for the classification of algebraic varieties in general to be able, so the ampleness of the canonical class is sort of very relevant for the classification. So canonical class, just a vector in some space, and then you have two cones, the ample, the effective cone. If kx is in the ample cone, if kx is ample or very ample, then we have Fano varieties. Minus kx ample Fano, kx ample general type. The pluses and minuses have to be interchanged, and otherwise x's of intermediate type. I guess, yeah, getting hot. This is minus kx ample, this is plus kx ample. So more advanced classification schemes based on the minimal model program or on Campana's program, so will be explained in later courses. All right, good. So Fano varieties. So minus kx is ample. All right, P1, the canonical class is 2 times the hyperplane class. Not much choice. Elliptic curves and curves of general type of genus bigger or equal than 2. In dimension 2, again, we have P2 and P1 cross P1. These are sort of the obvious candidates. We have hypersurfaces of small degree, so the degree is smaller than the number of variables, our cubic surface as before, and an intersection of 2 quadrics in P4, so 5 minus 4, it's again positive. So Fano surfaces are called Pilpezzo surfaces for historical reasons. And then we have K3 surfaces, for example, with degree 4 hypersurface in P3, and then products of elliptic curves, for example, abelian surfaces. And surfaces of general type, well, if the degree is allowed to be larger than the number of variables, well, then the degree could be anything. So it's a zoo. So there are no limits here. And that's why I just put ... I mean, the classification of surfaces of general type, you know, say bounded dimension, bounded degrees, is quite an active area of research. I mean, it goes back to the classical Italian algebraic geometry, but there's a huge literature on that. So special cases, special families, how many singularities are allowed, and so on and so on. Anyway, a big achievement of classical Italian algebraic geometry, but completed by Iskovsky and later Mukai and Mori, was the classification of Fano threefolds. So threefolds with ample anti-canonical class. So here we go. There are 100-something families. In fact, this classification was done sort of simultaneously with the sort of implementation or development of this minimal model program. How do you go about classifying algebraic varieties in general? And in that program, you also need to keep track of or to allow certain singularities. So there are also lots and lots of families of sort of Fano threefolds with singularities, and so then you classify those and so on and so on. So it's a very active field, and if you like, what's emerging here, we only see to dimension 3, but the theorem of Mori together with, I guess, Miyaoka is that, in fact, in all dimensions, the number of families of Fano varieties, like smooth Fano varieties, is bounded. So there's an explicit bound which is like exponential, something like even more than exponential, like n to the n, maybe even more, which says that, well, in dimension n you have at most so many families of Fano varieties. So you should think of these Fano varieties as being like atoms, like basic sort of structures in algebraic geometry. And of course, the same is hoped for Calabi-Yau varieties. But this is much, much less clear. So the physicists got interested in Calabi-Yau varieties. It would be a degree 5 hypersurface in P4, for example. Yeah? And there are several thousands of families in dimension 3, so explicit families realized as hypersurfaces in like products of projective spaces, weighted projective spaces, and so on and so on. So this was relevant for their physical considerations because somehow Calabi-Yau varieties made it into their view of the world, and then their geometric properties became relevant for, I mean, in string theory, and so I mean, if you search on MathSciNet for Calabi-Yaus, I mean, you get tens of thousands of entries about that. Anyway, so, and same, like for general type threefolds, again, if you don't bound the degree, you can get a lot. So the obvious questions are just look at this classification table. So what can you say? So the case of curves, so P1 and forms of P1 you understand. Well, elliptic curves, very rich arithmetically. Curves of general type, you have a result, proof of Mordell's conjecture due to faultings, that there are only finitely many points over number field. And then you can extrapolate from that, and the general conjecture, yes, going back to Bombieri in the case of surfaces, and to Lang, who we mentioned in the first talk, and then in a more precise form to Voigt, that if X is of general type, then the rational points are not the risky dense. So now we're working for a number field. Now, if X is Fano, so then one would like to conjecture that perhaps there exists a finite extension of the ground field so that the points are the risky dense. And in the case of varieties of intermediate type, well, we don't really know because we're just collecting information at this point. But Campana, as I said, has a precise conjecture, and so according to Campana's conjecture, every K3 surface over a number field should have this property. Every Calabi-Yau threefold should have this property. So even getting examples for Calabi-Yau threefolds would be interesting. So for K3 surfaces, so far, there are results by sort of Bogomolov and myself showing that if the K3 has some additional structures, like an elliptic fibration, or an infinite group of automorphism, so that would apply if the rank of the Picard group is, say, at least 2. So, in fact, if the rank is bigger or equal than 3, there are only finitely many exceptions. Then we can show that rational points are potentially dense. But in rank 1, geometric rank 1, it's very difficult. So, over number fields. And last year, Hassett and I proved that potential density holds over function field, complex function field C of t, for a general quartic surface in P3. So if you take a general quartic over a function field C of t, then you have potential density of rational points. So anything in this direction, say for Calabi-Yau threefolds, for special classes of Calabi-Yau threefolds would be very interesting. In this course, so we'll focus on counting points, so counting points and trying to relate them to geometry. So we need, of course, risky density, because if points are on subvarieties and you're trying to find connections between the geometry of the variety and asymptotic properties, I mean counting points, then you're only picking up the geometric properties of a subvariety, not the geometric properties of the whole variety. So the risky density is sort of the first input that you want. Otherwise, you're just looking at some lines on the cubic surface, and your asymptotic tells you something about the geometry of lines. In any event, so proving the risky density is rather tricky. The most interesting cases for us are varieties which are close to being Fano, where we somehow expect many rational points, and Delpezza surfaces becoming rational after a finite extension of the ground field are of particular interest to us. Now, Delpezza surfaces. So we have forms of these surfaces over a non-closed field, over number fields, like cubic surfaces without any points at all, for example, as we have seen, even failing the Hasse principle. But you know that if a cubic surface has like one rational point, then immediately it has infinitely many. So there is a geometric way of seeing it, just drawing lines and using, some kind of, it's not a group structure, but it's almost like in the case of elliptic curves, you draw lines from a point, there are 3 points of intersection, 2 points, you get a third. Playing these kind of classical geometric constructions, you can generate many points on a cubic surface. But for example, a Delpezza surface of degree 1 always has a rational point over any field, and it is an open question whether or not there are infinitely many rational points in all such cases. And in fact, one could think that maybe there are the risky dense as well. So there, again, nothing is known. Yes? Yeah. So that's a conjecture, yeah. Yeah, that there is a subvariety that contains all of it. So finitely many dividers or reducible dividers. So those are stronger versions of the conjecture. Then you can ask, well, maybe there is a finite set of divisors, so that for any number field, rational points lie on these divisors. However, of course, I mean, you can put a point anywhere. I mean, yeah. So maybe you want to say something else. I mean, you can always put an algebraic point outside the divisor. Yeah. Well, that's what I'm saying. You can always put an algebraic point outside the divisor, like one point. But you could say, well, maybe apart from finitely many points, all the points are on a divisor. These versions are possible, okay? And those are stronger versions of length conjecture. You can always put, some points passing to a finite extension of the field. You can always put a point outside the divisor. Yeah. So then the question is, look at curves. Can you bound the number of points on a curve depending on some invariance of the curve maybe or on the field, or independent of the curve, just depending on the field? So yes, in fact, this has been investigated. So this goes in the direction like effective Mordell conjecture. Can we control the number of points? So there are relations between that and the length conjecture in higher dimensions. So you can show if the length conjecture is true, then indeed there are very strong uniform bounds on how many points a curve of higher genus can have, depending only on the field or depending only on the genus. So there are various versions which have been investigated. But not relying on the conjectures, almost nothing is known. Yes? Yeah.
For a particular elliptic curve, is it always possible to extend the number field and get an elliptic curve with positive rank?
Yes, it's always possible. You can always make the rank positive, in fact, as large as you like. So we needed something like this in one of our papers. This has it for 1 billion varieties, so you can look up a construction there, yes. But there are many ways of seeing that, yeah. But that's, of course, you can make the rank as big as you like along finite field extensions for curves. All right? So, and, well, now that you asked it, so we looked at these questions of effective Mordell with Professor Bogomolov, who will be lecturing next week, for certain curves, hyperelliptic curves of genus bigger or equal than 2. And, so there are results that say, so every hyperelliptic curve has an étale cover which dominates one given curve, like y squared is x to the 6 minus 1. And so if you know anything effective about this particular curve, y squared x to the 6 minus 1, so anything towards effective Mordell, then you get it for all hyperelliptic curves. So, and the dependency is just taking into account sort of the coordinates of those points on P1 over which you have this branch cover, like the height, if you like, of the hyperelliptic curve in the moduli space. In any event, so effectivity issues are, yes, very interesting. Okay, so we've seen sort of the role of cones. I mean, we've at least defined effective ample cone or talked about it. Now, so this is how cones appear in geometry in this model program, in this classification. So assume we have a Fano variety with anti-canonical class in the interior of the ample cone. Then it is a theorem that the ample cone is finitely generated. So this is a big theorem of Mori. So he talks about the dual cone, about the cone of curves, and so proves that the cone of curves is finitely generated, while the ample cone is also finitely generated. Now, the ample cone is contained in the effective cone. The effective cone is a priori bigger, and if you look already in the case of surfaces, do some explicit computations, very easy to write down examples. But if using the minimal model program, which is a theorem in dimension 3, proved the following general conjecture, that if X is Fano, then the effective cone is also finitely generated. And then the generators are, well, elements of your lattice. I mean, don't forget you have the lattice, the Picard group, and then you have this lattice tens of the reals, and the generators of this cone are lattice vectors, and that means rational. All right, so it's known there for dimension 3, dimension 2 anyway by duality, ample and effective. And then the question is, so what kind of invariance do we get out of the effective cone? All right, so X moves projective, so projective, it's embedded in projective variety. We have a polarization L. Now assume that the effective cone is finitely generated. So So Fano and finitely generated effective cone, it's not equivalent. There are many examples of varieties with finitely generated effective cones which are not Fano. For example, hypersurfaces in Pn, n bigger or equal than 4, we've seen it before. I mean, the cone is what it is. It's finitely generated, but the variety is not Fano. In any event, we have a line bundle L, and we have a cone, and then we can ask, well, what's the smallest A, so that A times L plus the canonical class is in the effective cone. And that's some number. If the cone is rational, and that is spanned by lattice vectors, it's going to be, well, a rational number. And B of L is a codimension of the face on which this class, A of L times L plus Kx, will fall. Right? So we are on the face, we have a finitely generated cone, and we are on one of these faces, so we can speak of the codimension. Now, in the Fano case, so the anticanonical class is in the interior of the effective cone. So the picture is that the constant A of minus Kx is 1. So here we have it. So if you put minus Kx here, then 1 times this, and this is 0, and 0 is in the cone. And B is the rank of the Picard group, which I'm going to be using R for that. So A and B. So computing these cones explicitly is actually quite a headache. So for surfaces, that's one of your exercises for cubic surfaces. For three-folds, especially three-folds with, large ranks of the Picard group, like here, there is one variety well studied in other contexts. This moduli space of 6 points on P1. If you compute, the rank of the Picard group is 16, so you have a 16-dimensional space, and in it you have a cone. I wrote down sort of the number of generators for the dual to the effective cone because it's the dual cone that is going to enter our number theoretic considerations later on as well. The effective cone itself has 40 generators, and the generators of the dual cone, those are sort of the equations of the hyperplanes which are bounding the cone in the 16-dimensional space. And well, it worked, but back then it took, I think, several days of computer time to get it. Yes. So the question about the rank of the Picard group and about the effective cone, again, this question is interesting from the algorithmic point of view. While I don't know whether one should even expect to be able to compute the rank of the Picard group for a K3 surface effectively. I don't know. I expect that for Fano varieties, that rank can be computed. There is a finite algorithm for doing that. And then there should be some finite algorithm for computing the effective cone. And already in dimension 3, where we know that the cone is finitely generated based on the minimal model program, it should be possible to derive an algorithm in this direction. And again, it's a question to you, to geometers. So cones in geometry, but cones are like very basic objects, and one should not be surprised, they came up in analysis quite a lot. So in analysis, especially in homogeneous spaces, one often deals with cones that are not finitely generated, but rather sort of homogeneous. So like a cone, circle, for example, circular cones, and things like this, really. And then one can look at the Laplace transform of the set theoretic characteristic function of the dual cone. Now, to normalize the Lebesgue measure, I still keep track of the lattice. So I have a lattice, and I have a cone in the corresponding real space. I have a dual lattice, a dual sort of real space, and that will normalize my measure, and so I can look at this kind of integral. And the integral, will converge if the real part of S is in the interior of the cone I started out with. And that gives me some function. And for round cones, these are interesting functions like gamma functions, the products of gamma functions, things like this. And this goes back to Köcher, Rothaus, Winberg, and Farreau. And of course, a standard example is, simplicial cone, just the generators, R bigger or equal than 0, maybe generators EJ here, then the corresponding function is just 1 over product S1 to SR. So how do we see that? Well, the dual to a simplicial cone is again simplicial, and then that integral is just a product, and then you're integrating e to the minus x times s dx, and you can do that. So, and that's what comes out, 1 over s, and then you have a product. Now, let's look at finitely generated cones. So then, the first sort of observation is that the function, this alpha function of the cone, is in fact a rational function of a certain degree minus r. The degree is the rank of the lattice. So how do we get it? We look at the definition. So it's an integral over the dual cone. Now, if you start with a polyhedral cone, the dual cone is finitely generated. Again, finitely generated polyhedral cone, and then you just triangulate. So you subdivide your polyhedral cone into simplicial subcones. You can do that. There are many ways of doing it. And for each simplicial cone, well, after a change of variables, some linear change of variables, you get something like this. So you get a product of linear forms spanning your simplicial cone, and then, well, it's just a sum of such things. And of course, there are going to be cancellations back and forth, but you see the degree is sort of minus r of your rational function. You can pull together all your things, so this is what you get. Anyway, so what are the properties of, so it's a rational function. So we know that it's holomorphic in the interior of the cone we started out with, but as a rational function, it admits the meromorphic continuation everywhere. And then you have some poles, and then you can look at, well, what are the poles? And it turns out that if we restrict this function in several complex variables to one complex line, then you have a function, one complex variable, it's holomorphic somewhere, and there is a pole. And the pole is where? Exactly at this invariant A of L, which you define completely analogously to what we did before. And the order of the pole is B of L, and then you get meromorphic continuation to, in fact, A of L minus delta for small enough delta. So that's the story of the cones in analysis. Okay, now let's step back, start. Yes? Yes?
You have some fraction functions with sort of denominators of degree.
Yeah.
So why does that not give you, I mean, the linear forms might be very different, so why does it not?
That's right, there are cancellations. So, of course, I mean, so you have to sort of prove what I just said, that you have, so, all right, so here you have your cone, and so I shift it, and then I look at, so L, or, I mean, lambda, whatever I say. So again, so A of L was defined as the minimum number, so that L times A of L hits the effective cone. So that's a geometric setup. I'm just going to put it on the board. Now, in the analytic setup, I'm just computing this integral over the dual cone of E minus S A check, I guess, D A check. And then I said, well, one way to compute it is to just triangulate this cone, and then you have, I guess, a sum over finitely many lambda, maybe check some j, some finitely many cones, where you have a product of some linear forms depending on j and I will run from 1 to r to the rank of s, and so s here is a vector. Okay? And then the question was, well, all right, so what happens when you start putting this together? What happens with these linear forms, and aren't there cancellations? And in fact, there are cancellations. It's very funny to follow these cancellations through. So, so what happens is that so a priori we know that this function, just by the definition, so this is holomorphic for real part S in the interior of the original cone we started out with. But when we triangulate the dual cone, let's look at a subcone, like a simplicial subcone of the dual cone, then the dual to that will be bigger than the original cone lambda. So in fact, each of these terms is going to be sort of holomorphic in somehow a bigger cone. And then what you're seeing geometrically and analytically is that well, the common domain of holomorphy is somehow the intersection of these bigger simplicial cones. So this is what happens. And then, so these simplicial cones, the bigger cones in the original space, begin to cut out this complicated cone lambda. So that still doesn't show that as you go to the border of one of these, you really pick up a pole of order R. So that is, you show that. Okay, so I wouldn't be able to do it on the blackboard right now, but it's part of the theory of these things. Yeah. All right. So there are two ways to compute, therefore. Triangulation of the original cone, but then I'll show you another way to compute it later on, like tomorrow actually, where you get the triangulation of the original cone. And then the poles are actually obtained from cancellations in the interior. So you would have a sum of terms similar to that. And each term, they have like parasitic poles in the interior of your cone, and then there are cancellations between them. So, and there is also interesting combinatorics connected to this, now that you mention it. There is a notion of secondary polytope or secondary cone, namely, you could ask, well, how many ways are there to triangulate a given cone? And, well, you can see you pick some triangulation, you can move it a little bit, and it's sort of stable, but then at some point there is a jump. And so you can visualize that, well, these jumps, well, it's, again, some kind of combinatorial object, where if you wiggle a little bit, you stay in the same, and then there is a sudden change of behavior. So it's a combinatorial object, it's a polytope, the secondary polytope, and it has been studied in great detail by Gelfand, Kapranov, and Zelevinsky in their approach to hypergeometric functions. So this is sort of, yeah, where it comes from, all of this. In any event, now our number theoretical things, we have a number field, we have an algebraic variety over this field, we have the set of rational points, we have the delically-limitarized very ample line bundle. So what is it? So we have our projective embedding. After choosing bases in the space of global sections of our very ample line bundle, so we have sort of coordinates x0 up to xn, and then as we wrote down yesterday, a height is just maximum of the coordinates, if you like, or product over all v, maximum of xjv, and then you can change it at finitely many places, and that is a notion of an delically-limitarized line bundle. This is a delicatization, if you like. So we have a height. Over the rationals, just maximal coordinates. It depends on the embedding, and it depends on what you choose at finitely many places. The norms, square root sum of squares, maximal coordinates. And again, as I said, this definition, it's not invariant with respect to field extensions. In a later course by Antoine Chamberloir and also by Professor Ulmo, they will talk about behavior of algebraic points with respect to heights, and their normalizations will be different. So they will be sort of 1 over the degree of the field in those heights. Okay, and then there is a height formalism, and I just write down one of the properties: the sum of line bundles. The heights behave like this, so it's product of the corresponding heights, and I'm sort of putting under the carpet all the questions of what the metrization is on the sum and these kind of things. All right. Counting function, we pick some subset of the set of rational points, and then we count with respect to our height. And by projectivity, you can't have more points than on the ambient projective space. And on the ambient projective space, we wrote down there is an asymptotic formula, in particular there is a bound, b to the n plus 1. So finitely many, and then what's the asymptotic behavior of this finite number as b increases. The approach that has worked in many examples is via zeta functions, and in fact, so these are the height zeta functions, just a generating function as you would do in analytic number theory, you write the height of the point to the minus s, and then you sum over all points. Now, the projectivity, in other words, that bound we get from the embedding into projective space, will ensure that this data function is, or this series is convergent to a holomorphic function for real part s big enough. I mean, that is a given. So already somewhere far away we have a holomorphic function, and the question is, well, what's the analytic behavior? What are the properties of its data function? And there was a conjecture put forward by Butterfman, and so in one of the forms is that, all right, after finite field extensions of the ground field, so that's to ensure the points are Zariski dense, after passing to some Zariski open subset, that's to get rid of the accumulating subvarieties, which mess up the asymptotic behavior, the function should be holomorphic, in fact, in this domain, where A of L is that constant defined before and is on the blackboard. So we have the effective cone, we have ample line bundle is in the interior of the effective cone, the anti-canonical is also in the effective cone, Fano case, so you get the number A of L. And B of L, that should be the order of the pole at S equals A of L, and there should be some meromorphic continuation to A of L minus delta for some delta. In other words, the properties of this data function, like in one complex variable, should mirror the properties of this data function, this function appearing in the theory of cones. The restriction of this function to the line, so through L or lambda, if you like, should be, at least analytically, the behavior of these functions should be the same. So that's a picture. All right? And now what's the relation, again, to our original counting problem? Well, if you have a zeta function with some numbers there, and if you know that you have a pole, you have a function g of s holomorphic in some neighborhood of the pole, I mean, the real part as bigger than a minus delta, you have this kind of expression for your zeta function, then you can derive an asymptotic formula, n of b, the sum over all an's, n less equals than b, is, well, b to the a log b to the b minus 1, and then there's an explicit constant, and the relation between this and that, well, it's just the a is the location of the pole, which is bigger than 0, and gamma of b. All right? So that's a picture. And in particular, I write it down again, the asymptotic for the counting function, well, consequence of what we've discussed is that the asymptotic should be b to the a of L log b to the b of L minus 1, and then some constant, which we will discuss later on in bigger detail. All right, so there was this conjecture, and yes. Yeah. Yeah, so it doesn't matter. So if you like, if you work over the rational, the heights are integers, maximum of the coordinates, right? So, and an is 0 or 1 or 2, depending on how many points of this given height you have. So that's a connection. Of course, over number fields, the height need not be an integer, but sort of reasoning is the same. Now, so that was a picture, and of course, yes?
Is the divisor that you use to polarize the variety for the cone side of things the same as the, does that correspond to the line bundle you use to divide the heights?
So, well, I have a projective variety. So we have one sort of distinguished polarization from some given projective embedding. But it's also a theorem of Kleiman that in this case, the ample the classes, in fact, spans the Picard group. So, in other words, the ample cone is open. And I want a conjecture that takes into account like every possible embedding of my given variety. So that L that appears here has nothing to do with the polarization I start out with. So you have an X, you have a very ample line bundle L, one of the many that span the Picard group, Then you can write down a height. Well, that involves fixing some metrics. Then you write down the height theta function. So here it is. And then, to understand its analytic properties, you really need somehow the geometry of the cone. So the proper approach to this is really to look at all of these line bundles at once. And in fact, the way we will prove it, we will work not just with the lattice Picard, and not with the lattice tensor R, what's happening here, but we will in fact work with the lattice tensor C. So we will have functions on the complexified Picard group, and we will be interested in their analytic properties. And in fact, analytical, so we'll be using theorems from complex analysis in several complex variables, like convexity principle, which really which are based on the fact that you have several complex variables somehow. You need this convexity principle, tube domains, and things like this. And so tomorrow, so you'll see how that works. So it's really somehow to our advantage to have all the line bundles sort of together and simultaneously. And a posteriori, then we restrict to like one complex line in the space. So there was this expectation, and it was based on well, numerics. You take some standard surfaces, cubic surfaces, was based on what you had for hypersurfaces in many variables, the circle method. But there, the Picard has rank 1, and again, there's sort of very little to this kind of geometry. And then we had some examples like products of varieties, it worked, and some homogeneous varieties like flag varieties. However, a few years later, so Badrev and myself, we looked at varieties a little bit more complicated than what is the obvious suspects and choices. We look at a hypersurface and a product of P3 and P3, so a bihomogeneous form. So it's homogeneous in the x's, which is the coordinates here, of degree 1, and homogeneous in the y's, sort of degree 3. So this is your hypersurface. And it's Fano, because again, you sort of count the variables. In the x's, you have 4 minus 1, it's positive, and in the y's, you have like 4 minus 3, it's also positive. The rank of the Picard group is 2. The Picard group is spanned by hyperplane class here and here, restricted to x. So here they are Lx, Ly. And the ample and the effective cone, well, it's some simplicial cones, just spanned by whatever it is. And in any event, it's straightforward. You compute. So the anti-canonical class is 3-1. So a height on this variety, say over the rationals, would be like this. Pick the x's co-prime, and then you have maximal of the x's cubed, so it's this cubed, times maximum of the y's to the power 1, and less equals than b. So this is the counting problem of interest. So the anti-canonical height on that variety, so xy is maximum of the x's cubed times maximum of the y's. So, and then you want to count. I mean, what could be easier? Count how many x's and y's there are satisfying the inequality less equals than b. So why do I say it couldn't be easier? Because geometrically, this variety is not that complicated. So if you fix the y, and it just means projecting this variety to this P3. So if you fix the y's, you just have a linear equation in the x's. So over the space of y's, over that P3, you have a P2 bundle. So, and it's very easy to see this X is just a compactification of the affine space of dimension 5, A5. Everything can be parameterized. I mean, when you fix all the y's and then, some of those x's, you can solve for the other x. It's an affine space. So you're counting points on the affine space, but embedded in some strange fashion, in this fashion. So, okay, into a product of P3s. And, well, first of all, we don't have an asymptotic in this case. And even when you replace the 3 by a 2, it should be easier. In this case, you have to put a square here. Okay? But what we do have is the following. So b of minus kx is 2, right? The rank of the Picard group is 2. And so the asymptotic, according to this conjecture, should be b to the 1 log b to the 1, 2 minus 1. But in fact, if you restrict, that is, project to the axis, so if you fix the axis, then you just have a family of diagonal cubics of the form we saw before. And if the coefficients of those cubics are all cubes, for example, and if the ground field contains the third root of 1, then in fact these are split cubics. And a split cubic surface, as you know now, has rank Picard 7. And therefore, if the conjectures make any sense at all, for cubic surfaces you would expect b log b to the 6 from each such fiber. Those fibers are dense in the parameter space in the axis because the cubes are dense in all the numbers, and that's a contradiction in itself. So if the conjecture is sort of working for cubic surfaces, then it's not working for Vespano threefolds. But in fact, you don't need to rely on a conjecture. It's easy to show that without any conjectures, you get more than b log b to the 6, say. And using the recent results of Noam Elkis, you would even get b log b to the 6. So without conjecture, really, as a lower bound. Okay? We didn't have them back then in 96. But so far, so we've demolished the B conjecture with this example for now, but so far there are no counterexamples to this A of L. So it could still be the case that the number of points of L height bounded by B is B to the A of L plus epsilon. All right. Now, I should also say that once we saw that, we thought a little bit more about the geometry and about what the minimal model program would say about that. And there is actually a way to fix it and to get some correct, sort of, again, conjecture understanding on what should be happening. So now I want to focus on varieties where we have a big supply of rational points a priori. So how does it work? We pick some linear algebraic group, like a Heisenberg group, additive group, multiplicative group, or just PGLN, if you like, and you look at some algebraic representation. This acts on Pn, and then we just translate a fixed point in Pn of f by this group. So we have a height on Pn, as before, and then we can just look at, well, how many translates of x have height less equal than b. So here I should say right away there could be a stabilizer. It could very well be the case that you don't move at all. So in fact, then I would look at rational points on G mod h, where h is a stabilizer of the point x in this representation. And this is sort of a general principle. If you have some kind of automorphism or a group action, then well, it'll move your points around, so you get many. What's the translation into the geometric setup? Let's look at the Zariski closure of this. So this is an algebraic representation. So it's given by some polynomials. So the image is also described by some polynomials. Just takes the Zariski closure of the image. So you get some variety in Pn. That variety in Pn contains as an open subset, Zariski open subset, G mod h. And then, what else do we have? We have the standard polarization on Pn. So we have a very ample line bundle on this x. And it's G linearized, meaning that the action of G on G mod h extends to an action of G on the projective space. I mean, this is how we did it. I mean, we looked at the representation. We looked at the action through PGLN plus 1. And we have an adelic metrization just coming from fixing some metrics on O of 1 and this Pn. So here is our problem. Let's look at points in G mod h of f with height less equal to b. So that will be a big source of examples, varieties with many points. Unipotent varieties, compactifications of, say, additive groups or Heisenberg groups or upper triangular groups. So there is a way to compute the Picard group using the group action. Take any divisor, push it to the boundary. It becomes equivalent to a sum of boundary components. Are there any relations? The relations would come from functions without zeros and poles in the interior. But the interiors unipotent, so it's just the affine space. There are no such functions, just the constant functions. So therefore, there are no relations. So the Picard group is freely spanned by boundary components. You've computed the anti-canonical class, and you can prove that the effective cone is just simplicial, spanned by those components. Toric varieties, to be discussed tomorrow in great detail, are the same thing, except that now, yes, the Picard group is spanned by boundary components, but there are relations coming from functions without zeros and poles on the torus, and those are called characters. So you have an exact sequence, characters into span of boundary dividers into the Picard group. The anti-canonical class is computed, and the effective cone is spanned by the images of boundary components. Now, those cones are not simplicial anymore, because what happens, you take a simplicial cone spanned by these components, and you quotient it out, you project this cone with respect to some hyper, or with respect to some linear subspace. So you take any cone, and, well, it can be written in this fashion. Just take the generators of the cone, puts them in some space, and then quotient out by the relations between these generators. So any cone will do it. So there are some results. We'll come back to that. If X is one of the following varieties, flag variety, or an equivariant compactification of a torus, toric varieties, or a compactification of G mod U, you take PGLN, you quotient out by the unipotent subgroup, or additive group, or some other cases, then the height theta function has exactly the behavior we predicted before, behavior of this function. So the analytic properties of the height theta function and of this function are the same. And this constant C of L can be interpreted, it's a product of three numbers for a very specific line bundle, for the anti-canonical line bundle, where one of them is, well, this function invariant of this cone evaluated in the anti-canonical class, evaluated in a point in the interior of the effective cone. So beta is a non-trivial part of the Brouwer group that you've seen as well, Galois cohomology, and tau is Tamagawa type number. Again, we'll discuss it in detail before. Later in general, it's an infinite sum of such Tamagawa type numbers, where this is a fibration from the minimal model program of Fujita. So in all cases that I wrote down on the board here, this is exactly what's happening. So in all these cases, we get these analytic properties then, and we get this constant C as, well, product of three things for a particular class, for the anti-canonical class, and sum of numbers which we identify explicitly and define sort of what they are, and then identify the coming out of the analytic method of these kind of numbers. Okay? So we will have a proof in the toric case and the additive case on Friday, and then you will see how well, the analysis forces you to consider all these geometric constructions and to so this is an infinite sum in general. It's convergent, and all right. So here are some examples to finish. What are these constants? So for Delpetto surfaces of degree 4 over Q, so you find that non-trivial part of the Brouwer group, well, the only thing that can happen is 1, 2, or 4. So either your trivial Brouwer group or Brouwer X over Brouwer F is Z2 or Z2 plus Z2, and that's it. So for cubic surfaces, so Swinnerton Dyer found that, so these are the options for cubic surfaces. So you take a diagonal cubic surface, for example, x cubed plus y cubed plus z cubed plus a t cubed equals 0, with a not a cubed, then you get z3 plus z3. You take a general diagonal cubic surface, ax cubed plus by cubed, so you get z3. And in other cases, you get sort of z2 or z2 plus z2. So, and these constants alpha, which were the values of this function in the anti-canonical class, right? They have been computed, so for the Delpetto surfaces of various degrees by Derenthal, and then you get some numbers of this shape. Okay? So that's the big picture. Tomorrow we'll look at toric varieties in detail, and then you will see how all of this, for example, begins to appear out of analysis, very concrete and explicit analysis. And we'll look into these height zeta functions in more detail. Thank you.